In this video lesson, we'll be discussing air quality and major air pollution issues, particularly those affecting human health and the environment. In order to understand air quality, we will begin this lesson by reviewing the levels of the atmosphere, specifically those which are most susceptible to air pollution. This will be followed with air pollution definitions, which will allow us to look at both outdoor and indoor air pollutants. Finally, we will briefly touch on solutions to air quality issues and how we can reduce the effects of air pollution on us and our environment. The atmosphere can be broken down into 5 main levels. From lowest to highest altitude above the surface of the Earth, we have first the Troposphere and the Stratosphere. These 2 levels are where air quality is of most concern to human health and the environment. Putting it another way, this is where air quality hits closest to home. We will discuss these 2 levels in further detail in the next few slides, but for now let's talk about the 3 outer levels of the atmosphere: the mesosphere, the thermosphere, and the exosphere. These 3 levels extend from the end of the stratosphere to space. As such, we are not as concerned about air pollution in these levels, although they are still important to us in other ways. For instance, the mesosphere contains gaseous particles which collide with meteorites and other foreign objects. These collisions produce enough heat to vaporize those objects and shield the surface of the Earth from harmful impacts. The thermosphere contains most of the ionosphere, where gas particles are dissociated into ions by UV solar radiation, producing the aurora phenomenon and influencing radio wave transmission. Finally, the exosphere is the outermost layer of the atmosphere and fades into interplanetary space. Here, gaseous particles with enough energy are able to escape the gravity of the Earth and float off into space. The troposphere, stratosphere, mesosphere, and thermosphere are distinguished from one another by temperature inversions, that is, by a change in the lapse rate. The lapse rate is defined as the gradual change in temperature with altitude. These temperature inversions are depicted in the figure to the right. The M-shaped red curve is the temperature profile of the altitude of the atmosphere with respect to altitude, and the peaks and valleys are the points we define as the end of one level and the beginning of the next. Again, the troposphere is the lowest level of the atmosphere, closest to the surface of the Earth, and includes roughly 75 to 80% of the total air mass of Earth's atmosphere, and is a relatively thin layer, ranging from 5 to 11 miles thick. Using an analogy, if Earth were apple-sized, the troposphere would be about as thick as the skin. In general, the atmosphere is thinner at the poles and thicker near the equator, and this goes for all levels of the atmosphere. The composition of the troposphere is predominantly nitrogen gas at 78% and oxygen at 21%. The remaining 1% consists of water vapor, argon, CO2, and other trace amounts of gases and particulates. It is the makeup of the trace species which contributes to most of our air pollution problems. Even though they only make up a fraction of a fraction, a small change in trace species composition can have detrimental effects on our environment and climate. As a rule of thumb, gases in the troposphere become less dense with altitude and the air becomes thinner. Think about the difference between the air here in Ohio and that in Colorado, which is higher in altitude. Consequently, the temperature drops drastically with increasing altitude within the troposphere. Also of note is CO2 and other greenhouse gases, which play important roles in short and long-term weather in the troposphere. The stratosphere is the second level of the atmosphere and extends from 11 to 30 miles above the Earth's surface. The composition of air here is similar to that of the troposphere, but with only a fraction of the water vapor. As a result, most weather occurs within the troposphere, but some still occurs within the stratosphere. Within the stratosphere also is a very important ozone layer, which is located within the first 8 miles of the stratosphere. The ozone layer is considered as the sunscreen of the Earth because it keeps 95% of UV radiation from reaching the Earth. If it weren't there, we'd probably all be dead. Ozone also plays a very important role in the formation of free hydroxyl radicals. These hydroxyl radicals are considered the detergent of the atmosphere, because they react with many organic compounds to form stable end products that may later be removed from the atmosphere. Now that we understand the levels of the atmosphere, what exactly is air pollution? Well, air pollution may be defined as any chemical at a high enough concentration in the atmosphere to harm organisms or to alter ecosystems, human-made materials, or climate. As the saying goes, the difference between a trace species and a pollutant is in the dose. Air pollution can be broken down into two broad categories depending on the source of the pollutant. There are primary pollutants and secondary pollutants. First, primary pollutants are those chemicals which are directly inserted into the air by human activities or natural processes. A fancier way of saying by human activities is anthropogenic. Some examples of primary sources include coal-fired power plants, vehicle exhaust, volatile organic chemicals released by photosynthesis, among many others. Typically, primary pollutants can be broken down further into natural, mobile, and stationary sources. Try to think of some examples of these before the next slide. Secondary pollutants, on the other hand, are formed within the atmosphere through chemical, photochemical, or physical reactions. Typically, secondary pollutants are formed from primary pollutants, and this can occur either through direct means or indirect means. A strong example of a secondary pollutant is the formation of acid rain from sulfur dioxide emissions. Here we have a simplified figure of some pollutant sources. The volcano is considered as a natural source, whereas the car and coal-fired power plant are considered as anthropogenic sources. It should be noted that the formation of coal is actually a natural process, but becomes anthropogenic once extracted and burned for human consumption. The volcano and power plant could also be considered as stationary sources, and the car would be considered as a mobile source. The primary outdoor pollutants stemming from these sources include carbon monoxide, carbon dioxide, nitrogen oxides, volatile hydrocarbons, and primary aerosol particulates. Secondary pollutants include strong oxidants such as hydrogen peroxide and ozone, strong acids such as sulfuric and nitric acids, and nitrate and sulfate salts, as well as other secondary aerosol particulates. We will focus predominantly on the primary pollutants, but touch briefly on secondary ozone formation and acid deposition. Carbon monoxide and carbon dioxide are two outdoor air pollutants which can be grouped together as carbon oxides, although they have completely different functions as air pollutants. Carbon monoxide is a colorless, odorless, and tasteless gas that is typically introduced into the environment through anthropogenic sources, mostly through the burning of organic compounds. So, automobile exhaust, forest fires, and inefficient cook stoves are just several ways carbon monoxide can be introduced into the atmosphere. Carbon monoxide is extremely toxic to humans, and when inhaled into the body, carbon monoxide preferentially binds to hemoglobin sites where oxygen normally would, thus reducing the body's ability to take in and transport oxygen. Chronic exposure to carbon monoxide may lead to heart attacks and agitate asthma. Acute exposure may lead to headaches and nausea, mental impairment, collapse, coma, or death. Carbon dioxide is also a colorless, odorless, tasteless gas, but unlike carbon monoxide, most CO2 in the environment is a result of a natural carbon cycle. During this cycle, CO2 is respired into the atmosphere, which is taken in during photosynthesis and eaten by organisms, repeating the cycle ad infinitum. However, small contributions of sequestered, that means trapped, CO2 can have an exacerbated effect on climate. CO2 is the main greenhouse gas in the environment, absorbing infrared radiation and releasing it back to the surface of the Earth. Small increases in CO2 emissions lead to small temperature rises and may kickstart many different climate forcings. Anthropogenic sources of CO2 including burning of fossil fuels and deforestation. The next class of pollutants we will talk about are the nitrogen oxides and nitrous oxide. NOx is the notation used to describe reactive nitrogen oxide, and is the sum of nitric oxide, NO, and nitrogen dioxide, NO2, in the atmosphere. Nitrous oxide, N2O, should not be confused with the NOx species, as it is not closely related to either NO or NO2 within the troposphere. NO is a colorless gas, and NO2 is a reddish-brown gas. The NOx species are heavily interrelated and are constantly in flux. NO can react with oxygen, tropospheric ozone, and other free radicals to form NO2, and conversely, NO2 may dissociate in sunlight to form NO. So they're constantly in flux. NOx species have both natural and anthropogenic sources. Usually they are formed from the fusion of nitrogen and oxygen gas under intense heat and pressure, such as during a lightning strike or within an internal combustion engine. These species are seminal in tropospheric chemistry, but may produce excess levels of tropospheric ozone, especially in urban environments where traffic volumes are high. The NOx species may also react with volatile organic compounds to form photochemical smog directly. As we'll see in later slides, ozone also creates photochemical smog, and we've got a picture of that to the right. Looking beautiful city there. The nitrogen oxides may also react with water vapor to form nitric acid and nitrate salts. The main chemical sink or removal mechanism for nitrogen oxide is through this reaction with water vapor. Nitrous oxide, on the other hand, is released from fertilizers and organic wastes produced by burning fossil fuels. Nitrous oxide is a greenhouse gas and has a global warming potential of about 300 times that of CO2. However, not as much nitrous oxide is actually within the troposphere to make it a big difference. N2O is highly stable in the troposphere and is only removed in the stratosphere through reacting photochemically with ozone. It's actually also another ozone-depleting substances. We will finish up the major outdoor air pollutants by briefly discussing sulfur dioxide, particulate matter, tropospheric ozone, and volatile organic compounds, which I have touched upon previously in previous slides. Firstly, sulfur dioxide. Sulfur dioxide is a colorless gas with an irritating odor. As much as 90% of sulfur dioxide stems from human activities in urban areas. The major source of anthropogenic sulfur dioxide is emissions by coal-fired power plants burning coal rich in sulfur-containing compounds. Sulfur dioxide reacts readily with hydroxyl radicals in the atmosphere to form both aerosols and, in the presence of water vapor, ultimately sulfuric acid. Like the nitrogen oxide species, sulfur dioxide is a key contributor to acid deposition. Next, particulate matter. Particulate matter consists of solid and liquid particles light enough to remain suspended in the air. Particulate matter is usually characterized by its diameter size. PM10 designates all particles less than 10 microns in diameter, and PM2.5 designates all particles less than 2.5 microns in diameter. Larger particulate matter is usually of natural origin, whereas the finer particulate is of anthropogenic origin. The smaller sized particulate is able to penetrate further into the lungs, and some particulate may be fine enough to affect the cardiovascular system. To get a picture of the relative size of particulate matter, the figure on the right shows a strand of human hair with PM10 and PM2.5 superimposed on top of it. Lastly, ozone. Ozone is a colorless and highly reactive gas. It's a strong oxidizing agent in the atmosphere. Within the troposphere, ozone reacts with volatile organic compounds to form photochemical smog. Ozone is produced through a complex photochemical reaction involving nitrogen oxides. Thus, ozone is a secondary pollutant. Acid deposition is a secondary form of pollution whereby the three primary pollutants, sulfur dioxide, nitric oxide, and carbon dioxide, react with water vapor to form sulfuric acid, nitric acid, and carbonic acid respectively. However, this picture only depicts nitric and sulfuric acid deposition. You can imagine CO2 reacting similarly to these two pollutants in this case. The major sink of sulfur dioxide and nitrogen oxides in the troposphere is through dry and wet deposition. Dry deposition is a term used for removal of pollutants in the particulate phase by settling out of the atmosphere via gravity. Wet deposition is a term used for the washing of pollutants out of the atmosphere by precipitation events. The above image illustrates the chemical flow of sulfur dioxide and nitric oxide as these gases move through the atmosphere. Once emitted into the atmosphere as primary pollutants, these gases are first transformed into sulfuric and nitric acid through complex reactions with the hydroxyl radical and water vapor. In dry deposition, these acids are then carried by the wind until they either react with gaseous ammonia or other basic aerosols to form sulfate and nitrate salts. In wet deposition, these acids dissolve in rain or snow and are precipitated out of the atmosphere. Usually, whether dry or wet deposition occurs depends on local atmospheric conditions and present trace gases. Smokestacks are built to emit pollutants higher into the atmosphere so that they may be spread more evenly by the wind. However, they may perform differently depending on weather conditions like wind speed and temperature. Acid deposition is considered a regional pollution problem. It is not necessarily confined to the local area or even the area closest to the pollution source. In fact, air pollution is generally not an issue right next to the smokestack. The effects of excessive acid deposition are far-reaching and are not exclusive to the urban environment. Acid deposition breaks down statues and buildings, but can also create respiratory problems for organisms and humans, reduce soil pH, which may reduce plant biodiversity and make plants susceptible to disease, reduce pH of low or unbuffered lakes and streams, which are susceptible to changes in pH, and chronic acid deposition may reduce the pH of buffered lakes and streams over time. Acid deposition can also leach and mobilize metals in the groundwater, which can get carried off to streams, rivers, and lakes and bioaccumulate up the trophic ladder. The figure on the right-hand side depicts bioaccumulation, where trace amounts of mercury are consumed by smaller organisms and eventually accumulate into larger organisms. Think about this the next time you eat tuna or go fishing. The EPA and other organizations have fish advisories posted for your areas so you can see whether or not it is safe to fish in your area. This image was constructed by the National Atmospheric Deposition Program, NADP, using sites scattered throughout the United States. The NADP is a deposition monitoring network which analyzes both dry and wet deposition for many different pollutant species. Here we can see a spatial average of precipitation pH across the U.S. in 2008. Note the higher pH in the Midwestern and Northeastern states. Why do you suppose this might be? This image gives a crude depiction of pollution mortality rates in the United States. Note the high death rates in the Midwestern states and how closely this map corresponds to the previous pH precipitation map. Certain factors can alter the way pollutants travel and react chemically and physically within the atmosphere. Pollution may be decreased by dry deposition of heavier particulate, wet deposition from rain and snow, reactions with saltwater aerosols and air pollutants, wind dispersion, and chemical reactions of pollutants to a stable form. Pollution may be increased in several ways as well. In cities, slow wind speeds may reduce dispersion of pollutants. Hills and mountains may obstruct airflows in valleys, allowing pollutant buildup. High temperatures may promote unwanted chemical reactions. Excessive VOC emissions may increase the likelihood of smog formation. The transportation of pollutants from equatorial regions to polar regions may accumulate pollutants in the polar regions. And temperature inversions can affect the transport of pollutants in all spatial directions. So you may be asking yourself, what are some ways we can reduce air pollution? Well, the obvious answer is to shift to less polluting energy sources. But this isn't always an easy transition, nor is it always economically feasible. Other efforts to reduce anthropogenic emissions include literally taxing emissions or using a cap-and-trade system, using mass transit or carpooling to reduce vehicle exhaust emissions, inspection of car exhaust systems regularly, setting strict standards on emissions, burning low sulfur coal, implementing pollution control measures at the emission source, improving energy efficiency, and adding lime to neutralize acidified lakes and streams. In conclusion, air quality is not only a regional issue, but an issue on a global scale. Molecules in the atmosphere may have lifetimes ranging from mere milliseconds to hundreds or even thousands of years. Pollutants emitted in the U.S. may now reside over cities in Asia or Europe. The Earth and its atmosphere are extremely resilient forces, but humans and other organisms are a bit more delicate. I hope this lesson was informative and you have pulled away a greater appreciation and understanding of air quality as well as a new perspective on air quality issues. Thank you for listening.